All right, recording started. Let me share my screen. Okay, good afternoon. Today's lecture, we will continue on distribution substation. So in here in this picture, we have a substation that's converting high voltage to medium voltage. This substation converting 132 kilovolts to 33 kilovolts, or in other words, converting high voltage to medium voltage. So the first thing, the big one, is the transformer. This is called power transformer. Then after that, we have some measurement devices. So the first thing, which is basically this one, and we can see like there are three phases. So phase A, B, C. Then the first equipment after the transformer will be basically, this is called VT. And the meaning of VT, which means voltage transformer. So what's the difference between power transformer and voltage transformer? Power transformer is used to transfer the power and converting the voltage from 132 kilovolt to 33 kilovolts. In addition to that, supply power. However, voltage transformer is used only for measurements purposes. It's not used to power up devices for measurements. So we are using VT. So as a shortcut, we call it VT, which is used for measurement to measure how much the voltage on that transformer. And of course, we have three of those because we have three phases, so one each phase. After that, we will see the next equipment. This one, this is called CT, which is current transformer. And the purpose for that is to measure the currents. So VT for measuring the voltage and CT for measuring the currents. Then after that, we will see something like looks like a switch. This is called isolator or disconnector switch or disconnector. Then after that, this shape, the cylindrical shape, this is still also isolator, this one, which is called circuit breaker. Okay, so what's the purpose of the circuit breaker and what's the purpose of the isolator? Basically, the circuit breaker is used to trip the power or disconnect the power, and it can be used for in case of faults or case of emergencies like faults, or in case of manually, which is in case if we need to do maintenance, we will disconnect the power using the circuit breaker. So circuit breaker, as a shortcut, we call it CB. It's used to disconnect the power or trip the power when the power is energized. When the power is on, it will be turned off. However, the isolators, those isolators, the purpose for that provides a visual disconnection of the power. A visual disconnection of the power. What does it mean? Usually, the circuit breaker, we will talk, by the way, the circuit breaker in a separate chapter. There's a chapter about the circuit breakers. But anyway, usually the circuit breaker, when it's stripping the power will be when the power is energized. Power is energized, then it will trip it. So it will have a very high spark when you disconnect the power. So the circuit breaker comes inside like this cylindrical shape. Then the reason it's cylindrical shape because it's filled with gas or filled with oil that's absorb that spark because there will be a big spark. Again, we are talking about 132 kilovolts. So the spark will be very large spark. So you need to remove the spark or absorb the spark, then the circuit breaker must have an insulation material that's capable or can handle that big spark so it can absorb it. So therefore, it fills with gas SF6, or it can be filled with oil that absorb that spark. Then that's why make the circuit breaker distinguished from the others. However, the isolators, they are not supposed to be turned off the power. They're not supposed to turn off the power. They will be turned off or disconnected when the power is off. So what's the point of using isolator even though the power is off? Is just for an extra caution or extra, I would say extra backup to ensure for the maintenance team that the power is off. There is nothing. The power is disconnected, not only off. You can see a visual, provide a visual disconnection that you see the power is off. And it can be as a backup in case of the, I would say, circuit breaker failure. In case if there was a failure due to mechanical issues on the circuit breaker, the isolator, when it's being disconnected, they will see a big spark because of that. So the thing which is when it's being disconnected, you will observe that there is a disconnection, then it will be fine. So that's how the major components of the substation, and again, we will talk about this in deep details later as well. So here are some major equipments, as we said, like power transformer, circuit breakers, disconnected switches, bus bars, insulators. Then there is something we call a capacitor bank, and some others which is called reactors or reactor bank. So what's the usage? What's the purpose of using capacitor bank and reactors bank? Have you ever heard of those? Is there anybody heard of their capacitor bank, reactor bank? Okay, since no response, I assume nobody heard of those. So anyway, what's the reason for those? Let's recall the complex power. S equals P plus JQ. Okay? And recall the loads. The vast majority of our loads are based on motor based. Our load, motor based. And one of the equivalent circuit of the motors is the inductor. So it will be inductor based. That's our loads, inductor based. This means our loads are based on RL, which is resistor and inductive loads. That's our loads, and which make it lag. And the other thing, recall the power factor. Power factor, we used to say it's cosine theta, and we used to say this from circuits and power classes, which is P over S, or in other words, P over root of S squared of P squared plus Q squared. So the thing, once you increase Q, power factor will be low. That's something undesired, which making the power factor poor. So what's happening? When we have an inductive load or when we have a motor-based load, and especially during heavy load, when we have heavy load, what's happening? The power factor will be poor. Power factor is poor. Then we need to improve it. How can we improve it? It's poor because Q is high. We need to decrease Q. How can we decrease Q? Basically, recall the capacitor and recall the inductor. The inductor, we used to say it is J omega L or it is JXL. However, when we have the capacitor, we used to say it's 1 over J omega C or negative J times XC. Then when you observe, you will see the inductor has a positive reactance, the capacitor has a negative reactance, which make them opposite of each other. Opposite of each other. So therefore, in order to cancel the inductance effects, we need to install a capacitor or add a capacitor. And that's what's happening in real life application, especially in high voltage levels. When we have a high demand, a high load, what will happen? We need to decrease the inductance effects. And how can we increase it? By installing capacitor. Installing capacitor to reduce inductance effects. And this happening under heavy load. When we have a light load, it's not necessarily because inductance will be low, therefore we need to disconnect them. So as a result, we can say capacitor banks, there must be switched, can be switched on or switched off, depending on what? Depending on the status of the load. So they can monitor the load. If we have a high heavy load, it will be turned on. If we have a light load, it will be turned off. Okay, so now we know what's the capacitor bank. How about reactor? Reactor means inductance. Okay, what's the point of adding inductance? Let's make a quick recall for the equivalent circuit of the transmission line. Transmission line. Either if it's medium or which is called long transmission line, the equivalent circuit, we have a T model or pi model. So for example, the T model like this, or pi model like this. So in the equivalent circuits, you can notice there is a capacitance in that equivalent circuit. That capacitance can they can interact with the load. So I would say when there is a load that consuming inductance, the transmission line can compensate. The capacitance of the transmission line can compensate of that. So sometimes that's why under, I would say like medium load, there is no need to add capacitor bank. The capacitance of the transmission line will compensate of that, of the load, and will take care of it. However, if we have a heavy load, in heavy loads, the capacitance will not be enough to supply the reactive power. Therefore, we need to add a capacitor bank to compensate and recancel to improve the power factor. While if we have a light load, what's happening? And that's happening especially like in 400 kilovolts power lines in extra high voltage. Extra high voltage. So in this situation, what will happen? The capacitance will be very large value, and the load is very small. So this makes the capacitance of the transmission line way more than the inductance of the load. So as a result, the inductance of the load will not be sufficient, it's too small. Therefore, the capacitance is higher. As a result, this will make the power factor moving from lagging to be leading. Or we have extra reactive power that we need to remove it. That's something undesired. We need to remove it. So how can we solve this situation? By adding reactors. So you will add reactors to cancel the capacitance of the transmission line. Add reactor to cancel the impacts of capacitance of the transmission line. That's why we are using the reactor, and we are using it under light load conditions. So we can summarize it as follows. Light load, use reactor. Medium load, nothing. Heavy load, use capacitor. But keep in mind, this is not always I mean, it depends on the situation. We are doing several studies. So some substations doesn't need reactors. Some substations doesn't need some substations don't need reactors. Some substations don't need the capacitor bank. So it depends. Then the Department of Operation will do several analysis, like doing power flow, doing several real and reactive power compensation. Then they will decide if we need to install it or not. And if we install it, then we need to keep in mind there should be switches depending on the load status. Now, the other thing, let's go back to this substation. As we said, like we mentioned many things about it. Now, since we have CT for current measurement, VT for voltage measurement, and we have the circuit breaker information, then all of them, they will go on underground cables to the control room of the substation. So the control room of the substation, we call it switch gear. Switch gear, which is the control room of the substation. Control and monitor room. Monitor room of the substation. So there goes in like these pipes inside the substation. So they will be inside the building, indoor. Then it will be like this. So this is called the switch gear. This is switch gear. And by the way, again, there is another chapter about the switch gear. So we'll talk in deep details about it. But anyway, here just like I'm trying to explain the big image, then we will go in deep details one by one in the future I would say like lectures. Now, the thing here in the switch gear, what you will see the control of the circuit breakers, control of the isolators. You will see the monitor, this voltage, monitor the currents. In addition to that, you will see the protection. Like the protection, you will see something we call it relays. The relays, also we'll talk about relays later. So relays to detect or decide if there is a fault, they will monitor the voltage and the current. And if there's a fault, they will say, okay, there's a fault. Then once we realize there's a fault, the CT and VT, or like based on the measurements. And again, fault we mean there is abnormal operation condition. Then the relay will decide tell the circuit breaker to trip or not. And the other thing, there can be a fault like over voltage, overload, under voltage, like frequency, if there is a mismatch in frequency or over frequency relay, then several purposes. So they will detect. So the protection, the monitor, the control, all of them, they will be inside the switchgear. Now, let's talk about the typical configuration of the substations, like from the single line diagram. Here is high voltage to medium voltage level. Then, for example, this is 132 kilovolt side. The other side is 33 kilovolts. And there should be a circuit breaker for that. What's the point of adding circuit breaker? If there's something wrong with this transformer, the circuit breaker will trip. And the others who those lines are loads. So here's load number one, load number two, etc. There should be also a circuit breaker. What's the point of having a circuit breaker? If there's something wrong in load number one, the circuit breaker with load number one will be turned off. If something wrong with load number two, it will be turned off. Therefore, the other equipments, the other parts of the network, other parts of the circuits, they will not be impacted. If there's something wrong with line one will be out of service. Line 2 is still working, line 3 is still working, line 4 is still working, no other thing will be impacted. If there's something wrong with transformer number 1, then transformer number 1 will be out of service while the rest will be in service. So that's the point of adding circuit breaker. But when you look at it, there's not only a circuit breaker, there is isolator from each side. So every circuit breaker has two isolators. Is a must. Circuit breaker comes with isolators. What's the point of having the isolators? Again, they are called isolators, or they can be called disconnector switches. What's the point of adding these isolators? These isolators, again, as I mentioned earlier, they are provide a physical disconnection, a visual physical disconnection. So when you disconnect the circuit breaker, and if, for example, something wrong happening with the circuit breaker failure, then the isolators, both of them, they will work and isolate the system without, solve the problem. So extra condition or extra, I would say protection, or they can provide extra caution. That's the thing. So again, isolators provide extra caution, and they are not supposed to be turned off when the power is on. They will be disconnected when the power is off. How can the power will be off? Of the circuit breaker. The circuit breaker will turn off the power while the isolators will provide the visual disconnection. So again, whenever you see any circuit breaker, there will be comes with two isolators from each side. Now the other thing, here this is the typical substation for high voltage side. How about if we have a medium voltage, it will be something kind of different, a little bit different. So assume here we have 33 kilovolts to zero point 0.4 kilovolts. This is converting medium voltage to low voltage. 0.4 kilovolt, again, this means 400 volts, and 400 divided by root 3, it will be 230 volts. That's what do I mean by 400 volts or zero point 0.4 kilovolts. So this is the distribution voltage. Then this is a distribution transformer, we call it DT. Therefore, in the distribution transformer, the connection is kind of different. There is no circuit breaker, there is fuse. So that's the thing that we can monitor or notice. What's the point of using fuse, not a circuit breaker? Because of the cost. In my high voltage application, whereas like sometimes the switching can be frequent, more frequent, then basically we can say, let's use a circuit breaker. While in low voltage application, we will use a fuse because of the costs, which is cheaper than circuit breaker. Okay, what's the purpose of the fuse? A fuse, which is basically the purpose for that is overcurrent protection. Why overcurrent protection? If there is a fault going on, assume there is a short circuit fault. So when there's a short circuit fault, according to Ohm's law, V equals I times Z. Therefore, I equals V over Z. If there's a short circuit, Z will be 0, so I will be V over 0. Then the current will be infinity. That's theoretically. But in real life, it will be very large currents. So when there's a fault going on, and again, how can you calculate the fault currents? You can calculate it using what you learned from power system class, using symmetrical components. If there's unsymmetrical fault, if there is a symmetrical fault, there is another calculation by converting single line diagram to a per phase equivalent circuit and do the calculation. I mean, the fault current calculation, it's a separated course in power system class, but I would say it will be very large value. Therefore, the fuse is detecting if there is a very large value of the currents, the fuse will be heated, then it will be melted, causing disconnection of the power. Therefore, in order, if there is anything wrong going with the transformer, of the power transformer, then the fuse will be burnt. Then we will send the maintenance team there, solve the problem, then replacing the fuse by another one. That's the thing. That's how we are doing this. Okay, so in the medium voltage to low voltage, we don't have a circuit breaker, we have a fuse. All right, now we get it. Since we have a fuse and the fuse will take care of everything, what's the point of this switch? So again, we said the circuit breaker or the fuse will take care of if there's something wrong. But how about these switches? What's the point of having these switches since the fuse will take care of everything? The main reason for that is for the maintenance. Sometimes we need to do some maintenance, but the fuse is not melted, and we need to do some maintenance. Then you can disconnect the power manually by going there. So keep in mind, these switches will not be turned off, they will not be turned off if there is a fault. If there is a fault, if there's something wrong, the fuse will take care of it. But if we need to do disconnecting the power manually, doing extension, doing some maintenance, doing some other arrangements, then if you need to disconnect the power, we can disconnect it using these switches. But those switches are disconnected manually. They are not disconnected automatically because of the something wrong on the power. They don't detect overcurrent. They don't detect anything, any faults. What's detecting the faults is just the fuse. That's the goal. So far, we have learned 3 or 4 different things. The first thing, circuit breaker and isolator. Circuit breaker will trip in case of faults, and also you can trip it manually when you do maintenance. Trip it manually. Isolators comes after circuit breaker. So comes after circuit breaker just to provide a visual isolation. However, those two in high voltage, while in medium voltage, we have fuse that works only for protection, nothing else. I mean, it's not if there's a maintenance, you cannot disconnect the switch, the fuse. But in case if there's something wrong with the fuse, you can, for example, you can of course replace it. The other thing, the switch. The switch, it is used for maintenance or manual. It can be manual, turned on and turned off. So in case if there is a maintenance, you can work on it. So now it's your my goal or the thing is I want you to know the difference between the switch and the fuse, isolators and circuit breakers. It's very important. Now let's keep talking or keep browsing. Now in this part, which is we call it ring configuration, assume you have two feeders. Feeder number one or load number one associated with feeder two, load number two associated with feeder number one, and everything's fine, no problem in that. But the thing or the challenge, if there is something wrong, assume this line was out of service. Now, this caused load number one out of service as well because there is no power supply. The only thing that's supplying power is feeder two. But how can we solve it or how can we make it more reliable? Then here, there is a switch here. You can disconnect the switch. Therefore, the power can come from feeder one to supply line one and line two. So as a result, we can say we have a backup plan to have the power when we have this scenario. If feeder two is out of service, we can still supply load number one from feeder number one using the normal using that switch, which is called ring configuration. Now, that one again is used, in medium voltage. Now, how about in high voltage? In high voltage, this simple scheme, which is we call it single bus scheme. Here is the source, assume like here is the transformer. Now it's 33 kilovolts. Then it goes through a main circuit breaker inside the bus bar. This is the bus bar. Then from the bus bar, we have several lines. So each line will go to different city. So you can say like this is the line associated with the GJU. This line is associated with Madaba. And this line associated with Queen Alia Airport. Something like that. So each line will go to a separate thing. Then in here, we can notice that it's called single bus. Single bus, there is only one bus, and there's a circuit breaker for each line. Why there's a circuit breaker for each line? Because if there's something wrong of line, for example, like Madaba line, we will disconnect the power from Madaba. But we don't need to disconnect the power from GJU or from Queen Alia Airport or from the other cities. Then we can keep it for more reliable. Therefore, we need to have a circuit breaker on each line. So if there's something wrong in one of the lines, it will not impact the rest of the lines. That's the goal by having the circuit breaker on each line. Now, this single bus scheme is easy to follow, is cheap because it doesn't require a lot of cost, but the challenge, which is not reliable. What do I mean by not reliable? If there is something wrong with the bus bar, then the power will be off in everything. I mean, there is no backup on it. That's the disadvantage. But it's simple. Now the next scheme, double bus bar. Double bus bar, double breaker. Double bus bar because we have bus bar number one, bus bar number two. Double breaker because each line has two circuit breakers. This one has two circuit breakers. This one has two circuit breakers, and this one has two circuit breakers. That's why it's called double bus bar, double breaker. What's the point of having two? Let's assume there's something wrong in bus bar number one out of service. Then bus bar number two is sufficient to supply power. How about the opposites? Something wrong in bus bar number two, bus bar number one is sufficient to supply the power. So here in this situation, we have an extra backup. If there's something wrong with bus one, bus two will take care of it, and the vice versa. So that's something, that's the advantage of having double bus bar, double breaker. But the drawback of this one, it's complicated. That's the first thing. The second thing, which is basically the cost will be high. Look at how many breakers on the previous one. The previous one, uh, a breaker each line, four lines, four breakers. Here, we have four lines and two breakers each line, then two times four, which will be eight breakers. So we can say the breakers number of breakers is doubled. That's why it's called double breaker and double bus bar. Okay, so this one is costly. So which one should I use? Which one is the best? Double bus bar or single bus bar? The answer, it depends on the cost. Do you have money? If you have money and sufficient money, then okay, let's use double bus bar, double bus, double breaker. But if you don't have money and that area is not important, if you go to like some small towns, small cities, then maybe let's use the single bus bar scheme. While if you are in very important loads, for example, inside the cities where the loads are very high, then basically we need to use the double bus, double breaker scheme. And the other thing, which is when we are dealing with 400 kilovolts, most likely we use double breaker scheme. We don't use single bus scheme in 400 kilovolts. So it depends on how important the load is. So if it's very important, then okay, let's spend more money to make it to increase the security and to increase the make sure the system more reliable. If there's something wrong, the rest can work. While that's the other one. If the load is not that important, then why do we need to spend a lot of money on something not very important? The other thing, some modifications can be done to reduce the cost because again, double bus, double breaker is very expensive now. Can we figure it out a way to use two bus bars, but without doubling the breakers? Yes. Here is main and transfer bus scheme. Basically, we have a bus bar number one, bus bar number two, and we have single breaker on each line. But the thing, we add bus to breaker, bus tie breaker. So bus tie breaker can connect main and transfer bus bars together, and they can be connected or disconnected using this breaker. Other modifications, double bus single breaker scheme, which is very similar to this one, but the thing which is we are making it double bus. We have two bus and single breaker, such that each line has its own breaker. The difference between this one and the previous one, here the breakers between the buses, circuit breaker between buses, while here the breaker is outside the buses. So this one is cheaper because we are using only single breaker, double bus bar. But one of the things which is basically, if there's something wrong with bus one, bus two will work and the vice versa. But it's not as reliable as the double bus double breaker. The other one, typical ring scheme. We already talked about the typical ring before, which is basically if there's something wrong in the line number one, you still can supply power from the rest from the other side. If this one is wrong, then you can still supply the power from the other side. That's the thing, which is if from your right, if there's something wrong, your left still can work. Then the last one, which is a breaker and a half scheme. So a breaker and a half, it is a modified version of the double bus bar, double breaker. So we have bus bar number one, which is double bus bar. Now the other breaker, we can say for the upper line, we have these two breakers. For the lower line, we have these two breakers, which means this breaker is in two, common in two, which means the first line and the second line are sharing one circuit breaker. They have their own circuit breaker and sharing the other circuit breaker, which means two lines, we have three circuit breakers. So if we need to make it as a shortcut, one line, 1.5 circuit breaker, which is 3 divided by 2, 1.5. It's not, in real life, it's not one and a half, it's two circuit breakers, but the second one is sharing, therefore we can say, we can approximate it as a half circuit breaker. That's why it's called breaker and a half, which means the first breaker, their own breaker, which is their own breaker, and the second one is sharing the circuit breaker. That's why we call it sharing half of the circuit breaker. Okay? That's the sharing between the breakers. The breakers, that's why we call it one and a half circuit breaker. So again, the advantages, the single bus, lowest cost, but the problem is not convenient if there is a failure in the circuit breaker or if there's something wrong. If we need to do a maintenance, we need to do a complete shutdown. However, double bus, double breaker, the advantage is if we need to disconnect something wrong, the others will not be impacted. And if we need to do some maintenance, the other will not be impacted. There's no problem in that. But the disadvantages is it's very expensive. That's the thing. The other thing, which is we have, the best scenario, double bus, double breaker. The worst scenario, single bus. While the rest scenarios, like a breaker and a half, or double breaker and one break, double bus, one breaker, those are in the middle, intermediate between them. Which one is the lowest? Single bus. Which one is worst? Single bus. But again, as I said, it depends on the cost. Do you have money? If you have money, it depends on the importance of the loads, on the location of the substation. Is it located in very important area? Then we need to make a complicated design, even though we are spending more money, but it's for more reliable power system. However, if you are in outside of town, out of town, and the light is low, there is not importance. Therefore, we can use a single bus because it's cheaper. Substation cost. Substation cost really matters depending on the location. So, for example, the power substation in Abdoun and in the city center, different than the substation, for example, in outside on the suburbs, like for example, like in Zay or like substation on like very far areas where like the land prices are not very high. So when the land prices are very high, then we need to make sure to keep in mind the design more reliable, reduce the size as much as possible, to reduce the cost as much as possible. In addition to that, we need to make sure the power lines are underground cables. Like for example, in Adnoun substation, the power lines are underground cables. In the city center, the power lines are underground cables. In the University of Jordan substation, it's also underground cables. That's the thing. Then the other thing, which is the transmission line cost, as I said, like the cost depending on the area, the transmission line can be sometimes the overhead is cheaper, way cheaper than the underground cables. But if you need to purchase a very expensive lands and if you need to pay money for the landowners because using their lands to put power lines sometimes can be very expensive. Again, like if you are, for example, in Abdoun, if you are in city center, if you are, then you need to pay a lot of money. Therefore, it's cheaper for us to make it underground better than paying money for the landowners to establish a new power lines. The other thing, transformer costs. Of course, the transformer cost depending on the different things, how like the cooling process, the environment, depending on the size of the equipment, etc. The feeders and bus works cost away. Of course, this is really matters about the substation. How the substation will be? Do we need to make it indoor or outdoor substation? What do I mean by indoor and outdoor substation or aerial substation? Gas substations. We will talk about this later, not today, because it's very wide topic about the gas insulated substation, which is called a GIS, and air insulated substation AIS. AIS is cheaper, but it's very big in size, while GIS is more expensive, but the size is low. That's why Abdul substation is GIS, city center substation is GIS, while the rest of the substations, where when the land is very cheap, then we are using aerial substation. So according to ABB, typical substation can vary between 36 to 110 US dollars per kilowatt, depending on different circumstances. Here is an example from just Jordan University of Science and Technology. They have a substation, a small substation. That substation, in this substation, we have diesel generators. These diesel generators are working as a backup units. If the power is off, the diesel generator will work to supply power for the university and for the hospital, because there is a hospital, King Abdullah Hospital, that's associated with then this hospital, we need to have a backup generators. These generators can turn on to supply the hospital and supply the important loads in case if there is a power outage or if there is no power to supply the hospital and the university. The other thing you can browse, which is basically the transformer there, 33 to 11 kilovolts. So the 11 kilovolts will go inside the university. Then there will be a feeder that goes to engineering buildings, a feeder that goes to medical buildings, a feeder that goes to the hospital, and so on. So there should be 11 kilovolt feeders to supply different loads. Then near to each load, there should be an electrical room. That electrical room converting 11 kilovolts to be 400 volts or to be zero point 0.4 kilovolts. And again, 0.4 kilovolt or 400 kilovolt when you divide it by root 3 will be 230 volts. This is our utility volts or our home voltage. Here is also the scheme, how complicated is the system is with different areas. Now, the other thing, supervisory control and data acquisition. So we call it SCADA, SCADA system. SCADA, that's the shortcut, supervisory control and data acquisition. Let's recall at the beginning of today's lecture, I mentioned about CT and VT. And I said CT and VT are used for measurement purposes. They are used for measurements. And I mentioned also the switch gear. The switch gear to control and monitor. Now, we are using the switch gear to control and monitor, and we are using the CT and VT for measurements. Now we need to transmit this data to the control room. For example, in Jordan, the control room in Amman, Al-Mgabarin. So we need to move this data there. So we need to make sure to transfer these data in high accuracy and more safe, so there will be no hacker will come in and try to hack our system, and we need to make sure they will not be impacted. So when we are using the SCADA system, which is basically, it is allow us to monitor the electricity and control the electricity remotely from outside. So by making some serial communication channels using OBGW or line traps, we will talk about this also later. But the thing which is SCADA, we have a software that we can have access to control it. Um, then we can control the electricity remotely. We can monitor the substation remotely using SCADA control. But I mean, something that you can think about is, I mean, since they can be controlled remotely and we can control the electricity remotely, there is, I mean, a very, we call it a very big concern to have a cyber attack and to have hacking to our system. Then if they hack it, making cyber attack, they can disconnect the power from the whole country. So that's concern. Oh, do you think this can happen? Is there any possibility of that? There might be a possibility, but in Jordan, to overcome this risk or to avoid this risk, we have the control system for the controlling system of the electrical equipments and the internet is not internet, the normal internet that we have. We are using our own nets. We call it intranets, our own intranet or our own network, which is separated from outside, the internet to outside. So our own network is used to transfer the data from the substations to the control room and to control the circuit breakers and control the rest using the control room using our own network. It's not using the internet network. So we can avoid the cyber attacks, we can avoid any problems that come from outside. So therefore, by isolating this, we can guarantee there will be no outside disturbance, no outside hackers. That's the thing, that's how we are working this in Jordan. So again, the SCADA usually can convert the data and read it. So SCADA function, um, we can use it in reclosers, in synchronous check when you turn on and turn off the power, protection equipment of the substation, fault reporting, transformer loading balancing, voltage and reactive power control by adding shunt, by adding capacitor bank, turn off and turn them off, turn them on and off, turn the reactor on and off, equipment condition monitoring, data acquisition, status monitoring, data logging, and circuit breaker control. Here is like the diagram about the SCADA system. This is more in communication, more than electrical and power engineering. It's in communication lines. So communication lines that we are using, there are two types. There is the first type using one of the phases by using, for example, phase A as an example. So we can say in phase A, we know the power in 50 hertz frequency. We can add to it a communication signal. And that communication signal can be in megahertz or kilohertz. So they are in different frequency. So we can say here is the power signal and here's the communication inside it. Very small communication signal like this. So it can be the carrier, inside the carrier. Then the communication signal can be inside. At the end of the power line, there should be, I would say, high pass filter. Or you can say low pass filter, whatever you want to call it. So it will isolate the high frequency components and low frequency components. The low frequency component used to go to power up the signal. Because we know the frequency is 50 hertz, then it will go to the power signal to power up the devices. While high frequency, we understand this communication signal as a communication signal. Therefore, in high, which is called it high frequency, we'll isolate it. So, which is basically isolate this from this. So we just disconnected the signals, the power from communication. That's an old-fashioned, which is using one of the phases, which is old-fashioned. We are no longer using it. It currently exists, but exists in old power lines. Right now, in the new power lines, we're using another technique for communication, which is called OPGW. What does it mean? Which means optical ground wire. So there should be a ground wire in the power lines for if there is a lightning strike, it will absorb it. If there's something wrong, it will absorb the lightning strike and the others. So I would say in the ground wire, it has a strands. And inside it, we can put, which is another transmission line like optical cable, fiber optics, fiber optical cable. So from outside, it's a ground wire. From inside, it's a communication wire. And therefore, we are merging two, ground and communication, in something that's called OPGW. Then you can connect between the substation, between the control room, using the OPGW, which is optical ground wire. That's what we are using right now, and more reliable more than the filter that we use using line trap. That filter again, which is called used to called line trap. I know today we talked about too many concepts, too much concepts, but the thing about it, which is I need you to know the overall picture. Then in the next lectures, we will talk in deep details. So we will talk deep details about the isolator. We will talk in deep details about the circuit breakers, in deep details about the bus bars, about the transformer, deep details about CT, VT, how it looks like CT inside, how it looks like power transformer inside, how is the VT inside, how is the circuit breaker structure inside, which type of circuit breakers that we can use, which type of substations, etc. So again, there are many things that we will talk about it within this course. And here's the last thing about the configuration of the automation systems, which is basically we can see there is a computer, network master, and again, as I said, in Jordan, this network, it's our, I mean, regional network inside Jordan only. It's not going outside, then to avoid any hacking or any problem. Then we have the server, then we have input output digital relays for detection relays, etc. That's the SCADA system. Okay, now I believe we are done with this chapter. Next lecture, we will start talking about the distribution, overview about distribution system. Any question? Please, if you have any questions, speak. All right, since there is no question, let me stop the record. Okay, I just stopped the recording.